Hi everyone, this is Jung Ji from PhD Expertise. Today we'll have a chat with our special guest, Dr. Kaustubh Kaluskar. Dr. Kaluskar graduated from Indian Institute of Technology in Mumbai with a bachelor and a master dual degree in material science and engineering. He came to the US to pursue his PhD, also in the material science and engineering, under Professor Krishna Raja at Iowa State University. He's currently a researcher at a major energy company. Welcome to our channel, Dr. Kalushka.
Yeah, thanks, Jen. Thanks for having me, and really looking forward to sharing my experiences with you.
Sure. We'll start our first question. You were able to complete your PhD under 4 years. Can you share with us some of your major projects there?
My PhD topic was text-wise, it was like quantitative chemical imaging in atom probe tomography. What happened is that Iowa State University at that point of time, it still has then a microscope called atom probe tomography, and this microscope is used to recreate the three-dimensional distribution of atoms and ions across the samples. What it does is that it sort of collects lots of data. The data points are like millions of data points, and these data points represent the ions or the atoms in those samples. Now, my PhD topic or PhD research was mostly related to how we can make sense of this all this data which is being collected, and this data which is being collected. So each data point represents one atom and one atom or one ion. And what happens is that when this it is being collected, around half of the data points are being lost. Some of the data points, when they are recreated, there is some noise in the reconstruction, etc. So we can think of this final data as incomplete data and noisy data. The people from material science and chemistry background will know of things like TEM and SEM. So when you look at these materials under TEM and SEM, you can clearly identify, okay, here is a boundary. Here is a grain boundary, here is a precipitate, here is some kind of external material, and so on. But when we try to look at the material at atomic level, all these details are lost. So most of my activities during my PhD were related to coming up with rules that, okay, this is the boundary between two different phases and so on. So if we try to look at it from that point of view, what we are trying to do is that we have lots of data and we are just trying to find a boundary. So it can be think of it as a boundary when we are trying to do some kind of classification type of model building. Your data is distributed in a three-dimensional space, and you are trying to find a 2D manifold across that space. So that was the more or less of the PhD topic. I also worked on a part of, all of these calculations and analysis have some inherent uncertainty to it. So there was also an element of uncertainty quantification to it. And it was a combination of experiments where I was carrying out the experiment and collecting the data and then analyzing that data.
Looking at your resume, you worked briefly for a consulting firm before you returned as a postdoc at Indian Institute of Science Education and Research in Bhopal. Why did you decide to return as a work as a postdoc? And what were your research areas there?
In my postdoc, I worked on the atomistic modeling of materials, density functional theory, and time-dependent density functional theory. And the size of our materials is almost very small because these calculations are very computationally intensive. In time-dependent density functional theory, there is an additional element of time. So, for example, in density functional theory, I will mostly be interested in a stationary piece of material and how it will behave. In time-dependent density functional theory, I can think of that maybe I'm shining a light on a material and how will material response. So material responses is what comes into the picture. So that is what most of my work was focused during my postdoc, DFT and TDDFT.
Currently, you are a researcher at a major energy company, and you mentioned some of your main work is on data science. Can you share some of your experience for those people who are interested in starting a career as a data scientist? What's the best way to get started?
It will very much depend on at what stage of their career or their life they are. If they are a student, undergrad student or a graduate student, the best way will be to first of all get acquainted with some of the concepts of linear algebra and take some relevant courses. If I remember what I came to know about data science, that kind of thing I first encountered in my labs, where there were some in my physics labs and in my engineering measurements lab, where there were some projects related to how do you make sense of the data which is being collected in the experiment. At that point of time, the term machine learning was not that common or that famous. But looking back, I think that these maths courses, these lab courses, these are like the foundation of machine learning. Then once you have such kind of base in the theory, then of course you can start by doing some kind of toy problem. That is always very helpful. However, I must say that the problems in real life which you face are very different from these toy problems. For example, this is a cliche, but it's very much true that most of the time when you are working in the data science, most of your time is spent in getting the data, cleaning the data, understanding the problem space. I mean, solving the problem is of course important, but if you don't understand the problem space, you can end up with a solution which is very accurate but practically impossible to implement or practically wrong. So, understanding the problem space will happen only when you start working on real world data. So, this was about the student. If you are already a professional, and I have quite a few friends who have uh, with whom I have discussed that they want to know more about how to get initiated into the field. I think the best way is you start by reading, some kind of introduction to any of the books, and with that introduction, start looking around your workspace. See where the data is being collected, how it is being used, and what types of questions are being asked and answer. Not to solve it, but just to observe it for some time, and then come up with a hypothetical question or with an hypothesis, and start with your domain. So you have a data science skill set little bit and your domain which is quite in depth, and then you try to marry them, and that's how you progress. That's my opinion how one should approach this.
That makes sense. And so you spoke a little bit about machine learning, and that that field enjoys a very broad definition. So, but what do you recognize as some of the core knowledge or topic areas to help people understand kind of how machine learning is segmented or the way to think about machine learning in general?
If I have a problem in mind, yeah, and I'm using machines to solve it, which is like the what we do as an engineers, hardware, software, anything. But if I can write down the rules on my own, and that software is able to do it, then it is not a machine learning. What I do in machine learning is write down the code to learn the rules. So maybe at the end of the day, it is still if and then, but where to put the if and then is not coming from me, but it is coming from the program which works on some type of data. So, for example, if I have a map in front of me, and if I have to look at the map and then write manually that take left, take right, it's the conventional way or the unmachine learning way. But if I write a program which on itself, just given a point A and point B, comes up with take left, take right, then it is how it is coming up is that is the machine learning. Initially, when we were not collecting so much of data, we had a very narrow view of our space. And for that narrow view, our own intelligence was sufficient. Now that we are collecting a lot more data in much more dimension at much more frequency, it is not possible for me to, analyze it and to come up with the rules and so on. And therefore, I need an automated way to analyze the data and to come up with the rules. So that is what is machine learning in my view.
Okay. Yeah, and then are there core sort of foundational areas that are within machine learning?
Yes, I will say so because every day we keep reading about a new type of neural net architecture, a new algorithm, a new data set, and an associated new benchmark. So it's like there is so much out there, but there is also a core on which all this is built. And I think the some of the concepts like how do you define accuracy, how do you define loss, how do you some of the statistical concepts like variance, like standard, like the bias variance trade-off, that kind of thing. So these things are really at the core of it, and anyone who is looking at it from a career perspective should have a good hold on these concepts.
Okay, and so transitioning to more of the, the example and the way to think about this. So you're working in the energy space and the chemistry field, just in general, not specific to your organization or anything like that. Are there some examples you could give of the types of problems you could solve? The map example was a nice one, but something energy related.
For example, there has been some work in predicting or suggesting new types of materials or chemicals for existing applications. And these materials and chemicals are more energy efficient, or they are more prone to recycling, or they are less intensive in producing, and so on. So just to give you an example, and this is an example completely not what I will call a conventional application. Some researchers worked on analyzing the text data, which has been published over the years in journals, and came up with a new class of thermoelectric materials. Here, there's a combination of you do a natural language processing on the abstracts, and then you come up with a new type of potential material which would have taken many years if it were to be done in lab. This work was, I think it is 3 or 4 years old work, which was published in a very well reputed journal. In the organic material synthesis, there are things like you can represent your molecules in terms of a particular type of architecture, and then you can come up with what are the possible synthesis routes from molecule A to molecule B. And lots of work is, of course, going on there. Most of this work is still in evolving phase, and therefore we think that it will accelerate in future, because when I say that, there was this work where the NLP was used to parse some of the journal articles. Now, if you think about it, that many of these papers over the years were not written keeping in mind that it will be used sometime as a training data. They were just written as text. But as we move forward and we start collecting data, keeping in mind that maybe this data itself will be useful for machine learning, then the pace of discovery will also accelerate.
Yeah, no, that's and that makes sense. I think in the battery space where I used to work with, there was a lot of work on that where they would collect lots of data over published literature and put it together to try to bring some insights to life that potentially weren't there individually in each of the individual papers, but hundreds put together. That was a possibility. So that's very helpful. Switching to another topic, we've observed that you are an author on many patents in the area of machine learning. What are some of the differences as being PhD students we think about and postdocs think about publishing papers versus patents, and some of the differences there in general?
the way you think about patent in many ways is very similar to the way you think about paper, but there are some key differences. Well, first of all, from as a PhD student, we are very much trained to go very deep into the topic and think about it from all the angles that maybe what happens if this does not work or that does not work and so on. We have to understand that patent is more like an application to a new area. So if there is a method, if there is an approach, maybe that method is already known in literature. But if that method has not been applied to an application area, then it's theoretically a patentable idea. That is how one has to look at from the application area, not from the methods perspective. And therefore, in industry, what happens most of the time is that you start by analyzing that what all things are out there. And many a times you find something which is out there, and then you make a decision that I'm not going to work on that. I'm just going to buy a subscription to that software or maybe collaborate with someone else to work on that. And then and sometimes it happens that you find that, oh, there is nothing out there. Maybe there is a method out there which can potentially be applied to my current problem, but so far no one has applied. And that is, in principle, a patentable idea. And that is how you should, or anyone should look at when starting on a new project.
Okay. So just a quick follow up there. What's an example of like a method, just to give some more context to the people listening?
Let's say, for example, you have an optimization algorithm, let's say, okay, and that optimization algorithm is probably well known that how it's some kind of optimization method, that how do you distribute some points across some area. That is a method. The theory is well known. Maybe there is a solver out there which does it very fast for you. Now, you have a factory area and you want to put in those lamps in that factory area. There are no dark spots and so on. And then when you go and try to look that maybe there is a software which can where I can just put in my coordinates and it can give you what are the best coordinates. But there is no such thing out there. So you use this method and then you apply for this particular problem area. And then it's thing you can say that, a method to identify the optimal locations for putting up lamppost. Of course,
Oh,
it's a
okay.
very elementary, naive example. I'm sure there are there are softwares out there, but just to give you an example that, how you take a method already published and apply it to a new application area.
Okay, and that's patentable then
That
as well,
is, in
potentially.
principle,
Okay.
patentable. Yeah, yeah.
Okay,
And
that makes sense.
but then again, I mean, the rules vary from country to country. In some countries, the softwares or algorithms are not patentable. In other countries, they are patentable. So,
Okay. And finally, we like to always close with some words of wisdom from from the people that we're interviewing. And so could you share any tips on continuous learning in this space? What are good resources to use to be able to do that?
I understand that continuous learning in the sense of machine learning, right?
Machine learning, yes. Yeah. Yeah.
Yeah.
So for us to continue to upskill in machine
Mm.
learning.
So since we are talking about the continuous learning part, I think there are two things here. First thing you have to know is what is happening in the machine learning. At the same time, you should also be very much engaged with your domain, because personally, what I have found is that when I started, I was applying machine learning to the first level of problem which I faced. Then, when I went a bit more deeper into the problem, I found that my existing knowledge of machine learning is not sufficient. I found some constraint or some new data set or some new difficulties for which my existing knowledge of ML was not sufficient. So then I went back and looked that which new method can be useful, what I need to change. And that's how it sort of reinforced that what I need to learn, what I need to look at. I think it is very much similar to how other techniques, other disciplines have evolved. If you look at things like, let's say, CFD, yeah, CFDs are numerical techniques where you solve a system, and you learn CFD and then you solve it on one type of problem, and then you say that, okay, now this is one type of problem. Now what if I introduce a second phase to this problem space? And that will require some modification in your CFD algorithm. So you will go back and improve on the CFD algorithms. And then you will say that, okay, now this is a second phase. Now, what if one of my phase is moving across the other phase, and then it will lead to some more improvement in your CFD algorithm? Similarly, in the ML space, unless you are into core ML research, in which case you are anyway aware of all the new things which are happening in the world. I think the best way is to, challenge yourself with new type of problems in your domain. So what happens is that sometimes we get content. Okay, this is the type of problem I have solved. I'm very much comfortable in it. So I'm going to limit myself to similar type of problem in future. But if we go deeper into the problem space, if we add more complexity to the problem, then that will itself motivate us to go and explore newer algorithms, newer techniques, and so.
Yeah, we appreciate that. And so we're out of time, and we want to thank Kaustubh for his time today. It's been a really great conversation, and we hope you loved the lamp example. That was helpful in providing some clarity on what machine learning, the benefits of machine learning are. We want to thank Kaustubh, and if you have any questions for him, please send them to phdexpertiseteam@gmail.com, and stay tuned for our next episode. Thank you, everyone.